Hi, we will continue to discuss the use of BoneProfileR. BoneProfileR is both a method to study the bone compacity and a software to apply this method using bone section. The software is written in R language, can be obtained or as a R package or as a web application. The bone section is split in 60 pies and 100 concentric circles. Each of these 6,000 parts are characterized by a proportion of mineralized pixel, and a Bayesian model is then fitted to adjust this proportion over the distance to the center of the section. In the previous video, we saw the basics of BoneProfileR methods, and now we will analyze partial section and see how we can model the radial pattern of compacity or periodic pattern. Sometimes, especially for fossil bones, only a partial bone section is known. In such a situation, the automatic bone center detection cannot be used, and center must be chosen manually by the user. This is done using this function, BP choose center, and the software will wait that the user click on where is located the center. Then the function used to estimate compactness can be used using BP estimate compactness with the same parameters as we have seen previously, except that we should indicate that the section is partial using partial equal true. We must tell the software that the center defined by user must be used. Only the fast method is available. The accurate method cannot be used with partial section. And we have a new parameter that is important, which is number of remove edge for partial section. Here I use 5, but when you use partial bone section, you see that the edge of the section is not perfectly known, and to be sure to not take into account pixels that are outside the partial bone section, we will take some precaution to say that we should exclude the edge of the section. This is done with this parameter, number of remove edge partial. The highest is the number here. The more you exclude section to be sure to take into account only the correct section. Let's see here if we use 1, you see that we exclude only one very small part of the edge of the section. If you take 5, you exclude more part of the section. So you must check visually if the value that you have chosen is correct or not. Here we use directly 5 to be sure to exclude the part of the section that could be very close to the border of the bone, and we fit directly a maximum likelihood fixed model. We do not use first a fit with logistic and then fixed. We directly fit a fixed model with this key 1 and key 2 parameters that are specific to fixed model. Then we use a Bayesian version of this model, and we can plot the results, and we plot the fitted models here according to the observation of the compactness here. We can see something that could be strange at first. You see that this model goes from 1 at the periphery, perfect. You have a steep change of compacity, and after the model is relatively stable until the center of the bone. You don't see, as you could expect, something like this. Why? It's because here you are at the center of the bone. You are here. Here you have very few pixels. You have much more highest number of pixels at this part, and of course, the more you are at the exterior, you have more pixels. Then, when you fit the model using likelihood or Bayesian, you use a binomial distribution, and it takes into account the quantity of information you have. You have more information here than here. That's why the model finally is relatively stable from the value of around 0.9 from the center. The compacity is relatively stable along all this section. It can be strange, but this is expected and this is normal. And indeed, when you look at the compacity, you see that the compacity from the limit of the periphery here to the center is relatively homogeneous. This is what the model tells you. Now, let's see another function of the BoneProfileR. In the previous analysis, what we have done in the first video and what we have seen previously here for partial section, the compacity was fitted considering only an effect of the distance to the center. However, it is also possible that you have radial information in the bone. Some part of the bone could be more dense than others. Then it could be interesting to check if you have some radial information on the compacity. To do this, we can use two methods, or to model a periodic model of compacity or a radial model of compacity. Let's see first the periodic model of compacity. The compacity that we have fitted previously using a scaled fixed model used 6 parameters that have direct biological interpretation. The parameter P is the position according to the distance to the center with the largest change of compacity. S is the rate of compacity change at P. Mean is the average compacity at the center. Max, the average compacity at the periphery. K1 is a compacity transition toward mean, and K2 is a compacity transition toward max. Then we will add a periodic effect on each of these parameters. The generic name of these parameters will be X, and it permits to model a periodic change of compacity when you turn around the bone. This is done from a mathematical point of view by adding X sin and X cos parameters in the model. Then you can add 6 multiplied by 2 parameters to the fixed model to describe your new periodic model. We will do this. First, we fit a fixed model without periodic effect. This is similar code as what we have seen previously. and you see that we fit directly a fixed model. We do not go by logistic and then fixed. Okay, let's see the fitted parameters. With this function, get fitted parameters, and we have the values for P, S, min, max, key1, key2, and the standard error for each of these parameters. This is the uncertainty for each of these parameters. Then, now we fit the periodic effect using first maximum likelihood and then Bayesian. We take the fitted parameters of the fixed model non-periodic, and we add these two new parameters, sin and cos, for each of the initial parameters of the fixed model. Then we fit a Bayesian version of this model, and we can see the results. First, we can show the parameters periodic fit with this function. We have here the p-value fitted, and in x-axis you have the angle in radian. 0 is the horizontal right of the section, and this is a trigonometric circle. You see a very slight effect of p parameters. The p change a little bit when you turn around the bone. This is the effect for S, and you see also a slight change of S parameter when you turn around the bone section. Now that we have the parameters fitted with periodic effect, we can check what is the periodic model of compacity. This is done like this. We have the distance from the center. We are here at the center, here at the periphery. And you see that the compacity is larger at the periphery, nearly null at the center, and you have a zone with change of compacity that is not exactly the same all around the bone. You see that you have more so less dense bone when you are around the right of the bone, and it is more dense when you are more distance. We can show the periodic model of compacity. It takes into account both the uncertainty modeled by Bayesian, but also the change of P and S and other parameters when you turn around the bone. That's why the uncertainty of the curve is a little bit larger than when you use only the non-periodic model. Now that we have modeled the compacity taking into account a periodic effect, we can model the global compacity using the summary command with the bone section. You have estimation of compacity and linearized compacity. The compacity is simply the observed compacity. Linearized, this is equivalent of integration under the curve. We have seen this in previous video. Now, let's see another method, which is the radial compacity model. In this version, we model the compacity for each of the 60 sections, the 60 pi, and for each of these 60, we estimate a flexit model. Then we have 360 parameters that are fitted for this bone. We can make this analysis using this command, and we have the results here with P, S, min, max, key1, key2, the average value, the standard deviation, taking into account that from pi to pi, this is a little bit different, and then we can estimate the standard error. No Bayesian model can be fitted for this particular model. It will be too long. It is possible, but it will take days to get results. The results for all these 60 sections for parameters are shown here. I do not show key1 and key2, but it can be done using parameter name equal key1, for example. Now that we have modeled global radial compacity, we can estimate the global compacity using this radial information, and we have here the values for this model. In conclusion, we have seen two methods to estimate a radial pattern of compacity, or a periodic compacity with a single model for the bone section using a periodic trigonometric model for each of the parameters, or a radial model in which a model is fitted for each of the sections. Depending on what you want to do, the first or the second method could be the method of interest for you. Thanks.